it is very straightforward. So we label them this way: 1, 2, 3, 4, 5, 6, 7, 8, 9. And then after 9, we now rotate this thing counterclockwise. 10, 11, and so on, right? And then 16 here. So this is the thing we want to do for generic letters instead of specific numbers like 4. So assume that we have m sub-universe in one direction, so m sub-universe so total m sub-universe in one direction and n sub-universe in the other direction. Then how can we label these points? And we should do it. And exact position, exact xy coordinate system, coordinate point, and then index should have a match. In other words, index 1 should represent this point. So assume that we have 1, 1, 1, 1 domain. So 1, 1, 1, 1 domain, like this one. Then assume that we divide this by m, and then divide this by n. Then first position is exact xy coordinate is 1 over m, and then 1 over n. Excuse me. And 2 is 2 over m and 1 over n, and so on. It goes on. And then m minus first one is m minus first one is m minus second one. M minus second one is m minus 1 over m and 1 over n. And for convenience, let's call m minus n lowercase m. So it is defined to be lowercase m. So uppercase m and lowercase m has this relation. M is equal to uppercase m minus 1, and n is equal to lowercase n minus 1. And m represents the number of sub-universe, right? M represents the number of sub-universe. The next thing is this. So in this sense, it is m minus first one. M minus first one. And then m's position is 1 over m and 2 over n, right? 1 up. Do you follow me? So you should design this kind of thing. This isn't the only one, but I'm just suggesting you one example. Yes?
Up in the top left, we have 16.
Uh-huh.
Going back and forth once you start the next one.
Oh, it is not 16. Sorry. So I think it's 25. So it is a mistake. So let's do it. So thank you for the correction. So this is it. So we should find this kind of relation. Of course, as I mentioned, this isn't the textbook scheme, just giving you one example. Then m plus 1 is 2 over m, and then 2 over n. And then m plus 2 is 3 over m, and then 2 over n, and so on. It goes on and on and on. And then 2 times m plus, it's better to write it this way. M minus 1 position times 2 has this value. And we should find this kind of pattern. In other words, you should create this kind of routine in any possible way. This isn't the only way, but you should create this kind of system and then find the corresponding index. So once a point is given, for instance, for a random case, I over m and j over n is given, then you should have matching number n here, right? Matching number, I will use lowercase n. So this is the task you need to do. And then after filling these positions, total how many points, interior points? Total how many points? Total in this direction, m minus 1 points, and in this direction, lowercase n minus 1 point. Lowercase n, uppercase m equals m minus 1. Similarly, lowercase n is n minus 1. And this n is misleading, so I will use k, because n is used for other purpose, so I will use k. In any case, we can cover interior point. In other words, it goes on and on and on, and then m minus 1 multiplied by n minus 1 is the point having m minus 1 over m, and then n minus 1 over n. I will replace this by better writing. So this is the task you need to do, and if you don't understand how to do it, or if you don't have any idea about this step, ask me. I don't have any reason to hurry, because right after this is designed, we are almost there to finish this thing. So if you have any questions up to this point, ask it. So I have a question. What direction do you think is easier? From ij to one index, or from one index to two indices? What do you think is easier? Usually, two indices to one is easier. In other words, you run program for ij, and then for each ij, you calculate the correcting number. That direction is easier.
Can you just use the same one in reverse? I mean, you have to go
No problem. Any way is possible. As far as you match these things. Oh, you mean this is the other direction? Yeah, it's possible. Yeah, it's possible too. But anyway, it's okay. You shouldn't order points this way either. In other words, you can order anyway. I will let you know just one or two examples. If you don't like this order, you can order this way. So I can order this way. 1, like 1, 2, 3, 4, 5, 6, and then go up to like 10, and then 11, 12, and so on, right? So you can order this way if you want, right? So you can order this way, or what else is possible? A lot of possibility. You can order spiral way, right? Or from inner to outer, right? So anyway, it's possible. As far as you represent the two indices or position using just one number, then anything is okay. But roughly, as I mentioned, the easiest way is assigning the meaning of i's position and then j's position, and then the actual meaning is the point in the domain. Point in the domain is I over m, and then j over n. Why do we need this thing? Because computer uses indices, right? Computer uses indices, but actual position is not this indices. It's just the real position. This is the actual position. These are indices. So we are using indices, but meaning is this one, this position. Then I represent the, you can make a formula, so I will let you know how to make a formula. From this, can you determine the index? Then it shouldn't be very difficult. Why? Usually, in my design, in my ordering, not spiral while going back and forth, if we follow my design, if these are all interior points, ij are all interior, these are all interior points, then this is very easy to determine. J represent heights, right? I represent offset, right? So offset and heights are mixed together. How? If J is given, then J means J minus 1 heights, right? And then multiply by n minus 1. Do you follow me? Sorry, just a moment. M. Sorry. This height means we are advancing this much, right? Because if you go all the way, it is m minus 1 points, right? And the next m minus 1 point, next m minus 1 point, next m minus point. If you have first row, it doesn't have any lift, so it just have 0 lift, right? 0 lift, but it has 1 lift. That means that we already wrote down m minus 1 points. Do you follow me? So lift is represented by this one. If you have just first one, then there is no lift. In other words, only offset determines the position. But if we have like 2, then this means we have lift 1, right? We have 1 lifted quantity. That means all the numbers here is written. Then this plus I will determine K. So there is a straightforward relation like this for interior points. If you don't follow me, ask me. So you can use this idea to find the index. Once ij position is given, you can find one index. How? This second one represents lift, right? After writing all the numbers, we have the lift, and then all the numbers are written and lift, and so on. So each row has m minus 1 numbers, right? M minus 1 numbers in the first row, m minus 1 numbers in the second row, and so on. So we don't have any lift in the first row, so 0 lift. But we only have offset, right? We have offset. I offset. So that represents the point, the index, right? So do you clearly get the idea or not? Then how can you really program these things? It's not very difficult. I will show you the program too, portion of this program too. So if for I running from 1 to, I should run from 1 to n minus 1. M minus 1. And then J running from 1 to n minus 1. And then vertex usually k is equal to 0, and then k is equal to, because MATLAB uses first index, so let's say index, and then vertex k equals I'm confused. Sorry for the mistake. This is not good design, so I will write it differently. Vertex, the number that I wrote down, vertex I plus j minus 1 multiplied by m minus 1, which point, right? Is this correct syntax or not? Or parenthesis correct? I think it's parenthesis, right? Parenthesis equals I over m, and then j over n. In other words, vertex position is determined. And then we finish the loop. So if you have a question up to this point, ask. In other words, once we pick some number, then we have a matching coordinate, right? So matching coordinate becomes a number by this routine. And if you doubt, you can check. So now vertex information is stored. Then let's really run it like a computer. It's 1, 1, I equal to 1, j equal to 1, then vertex of what? If ij is 1, 1, then vertex of what? 1, right? So vertex of 1 is what position? 1 over m and then 1 over n. Do you follow me? Now vertex 2, I is equal to 2, j equal to 1. Ooh, it doesn't matter, but it doesn't matter theoretically, but usually it's a good idea to make the program intuitive. There is no big difference between the two, but usually writing it this way is better, because this way we can track down the individual assignment, right? I'm not saying mine was wrong, but I'm saying this is more intuitive. Then next time we advance J. We use all the possible offset and then lift instead of lift each time. So it's better to write it this way. So the next one is I is equal to 2 and j is equal to 1. If I is equal to 2, then 2, and then vertex 2 is what? 2 over m, and then 1 over n. And then 3 and so on. We go all the way and then assume that I is equal to m minus 1. If I is equal to m minus 1, then m minus 1 over m, and then 1 over n. Now, if we have j is equal to 2 and I is equal to 1. J is equal to 2 and I is equal to 1. Then what happens? J is equal to 2, it means lift. So it goes up. Then it happens this way. I is now 2, and then j is equal to 2. I mean 1 and 2, right? I is equal to 1 and j is equal to 2. And so on. So it covers all the numbers, all the interior numbers. And if you have a question, ask me. Then similarly, boundary can be determined. You still have doubts or you have difficulties? I don't know whether you completely know this idea or not. I'm just going through the interior using routine row first method, right? We follow row by row. So I varies from 1 to m minus 1, right? 1 to m minus 1. And j determines the lift. And eventually, we can determine the vertex position. For instance, give me ij. Give me any ij. Like, so let's just say m is equal to 10 subinverse, n is equal to 10 subinverse. Then, what is 5, 5? Can you find 5, 5? Vertex of something equals 5 over 10 or 5 over 10. So can you find the matching vertex using this formula? What is it? Can you find it? When I is 5, j is 5, what is it? M is 10, then lowercase m is 9, and then m minus 1 is 8, right? Similarly, n is 9, m minus 1 is 8. Then here 8, and then 5 minus 1, 4, and then here 1. And 30, right? So vertex 33 is 5, 5. So this completely handles interior vertex. And if you have a question, ask me. So this is the way we automatically assign appropriate vertex number for the two-dimensional coordinate system.
I is 1 there?
Sorry. 5. So 37. Right, 37. So 37's vertex is 5, 5. Let's really check it. 1, 2, 3, 4, 5, 6, 7, 8, right? 8, and then 9, and then 16, right? And then 17, and then 24, and then 25, 32, right? 32, and then 33, 4, 5, 6, 7, right? This is the point, right? This is 1/10, and then, right, 2/10, 3/10, 4/10, 5/10, right? 1/10, 2/10, 3/10, 4/10, 5/10, right? So this is the position. So 37th position is determined. So this way, we can assign vertex number for individual coordinate or nodes, right, that we decide to use. Then, as you can see, boundary is way easier than interior. Why? After using up all the interior points of this size, I changed the page, so I will write down the number. So to this direction, we have m-1 interior points. To this direction, we have n-1 interior points. So after using up m-1 times n-1 interior points, then we can assign the next one here, right? And then 1 and 1 added, right? So it is like this. But as I mentioned, this isn't the only way. This is not a textbook way, so you can use any ingenious way of your own if you want, right? And then assign the vertex numbers. So like this. For now, I running from 1 to m, right? 1 to capital M, all the way, because we are not worrying about interior anymore. We are running through the first one to the last one. So from 1 to the last one, m. M plus 1? Let me check. We subdivide by m, first one, second one, and then m plus 1. Do you follow me? Assume that we have two subuniverses, right? We have two subuniverses, then the points numbers are 3, right? So we should go all the way from 1 to m plus 1. Then, for these things, vertex m minus 1 multiplied by n minus 1 plus I equals I over m let me briefly think about I minus 1 over m, and then 1 over n. 0 over n, so 0. It's a boundary. So I was confused between the interior and bound. 0. Do you follow me or not? So this way we can fill the boundary row, right? Boundary row, bottom row. Any questions? So you should not be confused between the index and the actual position. It's boundary, right? So y coordinate is 0, and then even x coordinate could be 0 or 1, right? It's possible. So please check whether you completely understood this idea. Boundary is right here. The left-hand side. So we completely fill the boundary. And now I will use counterclockwise orientation. In other words, I will order this way, and then this, and then like this, right? I will order this way. I order this way. So the next one is, after filling all these things, so it is, as you can see, not the best design, but for this problem there is no difficulty if we do it this way. Then we used up initially n minus 1 times n minus 1 points, right? And then now we used up m plus 1 more points, but it's not used, so this m is replaced by m plus 1, right? And then plus 1, so m plus 2. So total number that we used is, if we add these kind of things together, m minus 1 times n after adding these things, and then plus 3. So I added m, I write it this way. This is written m minus 1, and then plus 3, and then m minus 1 and m minus are common factors. I factor the common factor n minus 1 plus 1 is n, and then plus 3. So we used up these many numbers. Right? How many? Initially we used all interior points, and then more points we used. I feel very strange. That should be, is 3 correct? Should it be 2? Right, right. Very strange. Then what is my mistake? I used up these many points for the interior, right? And then I used 1, 2, these many points. So total m plus 1 points were used. Then it is lowercase m plus 1, and then m minus 1 plus 3. Then it can be, what is wrong with this design? Do you find any?
Oh, you didn't factor it right. You didn't factor out the m minus 1 correctly. Right?
M minus 1 are factored out.
Right, and you get that times n minus 1 plus 3, which is n plus 2.
let me check one more time. Take a look. M minus 1, this is interior number, right? And then here m plus 1 points were used, total m plus 2 points were used, right? And then now I write it this way, m minus 1 plus 3. Then if we factor this out, then m minus 1 is the common factor, and then n minus 1 plus 1, and then plus 3. So m minus 1 multiplied by n plus 3. That's strange, I feel very... I think, oh, m minus 1 plus times n plus 2 is my guess. But calculation shows differently. What is the reason? What do you think is the reason? One, two, m plus. I do not understand why this is happening, but if you find the reason, please let me know. Because if one is off, then we are in trouble. So let's use a small size example. Did you find the region? A small size example might help us. This is a good example, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? 11 is the whole number. But now we have m minus 1, that is 3 multiplied by 2 plus 1, 3, and then plus 2 is 11. So this should be 2. So something is wrong in my design, but I cannot find the reason. Oh, the reason might be right here. 1. I think I might make a mistake around here. M minus 1, and then M. Total I covered 1 through m minus 1, m plus 1, total m plus 1 point. I don't understand why this is happening. Do you find a mistake or not? So take a look in our design. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 is 3 times 3 plus 2, 11. But my calculation gives us the result differently. I don't understand why this discrepancy is strange, very strange. Oh. Let me briefly check one more time. Here m is, we divide this by subinterval. We divide this by subinterval, 4 subintervals. We divide this by 3 subintervals. And then m is 1 less than this. And then n is 1 less than this. And then, now I know the reason. I completely considered wrong. My calculation was correct. M minus 1 is 3 minus 1, 2. And then n is what is going on? I think I completely messed up. I'm very sorry for my mistake. I realized my mistake completely. Sorry for my mistake. So I will return back to my design one more time and then correct it. Sorry. This time I will be more precise. So we have subuniverse M and subuniverse N. Then this means M plus 1 points at the same time M minus 1 interior points. This was my mistake. So this was my mistake. And then I conveniently wrote down lowercase m, and then I was confused between uppercase m minus 1 and lowercase m because there are m interior points. So I will completely correct my mistake. For interior, I used different numbers. For j running from 1 to lowercase n, right? Lowercase, I used n minus 1. That was completely wrong. And then 1 through m. Now we are using these letters. I was confused between uppercase and lower. This was my mistake. And then this gives us vertex position, and then shift I, right? This is the offset, and then j minus 1 multiplied by m. Instead of m minus 1, I used, oh, this is not square bracket. It should be parentheses. So please correct this part. In your writing, you have lowercase m, then replace it by uppercase. And then this equals now I over m, and then j over n. So you just correct this part, and then end. So now we can fix everything. So it's good to catch earlier than later. So please look at it. So I was confused. There are, m is the number of subuniverse. Then there are total m plus 1 points, but at the same time, m minus 1 interior points. So what I tried to say was m minus 1, but I was confused between lowercase and uppercase. And somehow I used lowercase here, meaning the uppercase, then it is completely wrong. So that's the reason why I was completely confused. So just remove -1, -1, -1 here. Then it will fix it. And then interior points is done. Then exterior points is total. There are m interior points in this direction, and a total n interior points in this direction. So m plus m times n interior points, right? These are all determined, right? These many points are all determined. So I was confused between the numbers. But if you have a question up to this point, ask me. Then all others are the same. Then the next one is for this boundary, for I running from 1 to m plus 1, and then vertex of m and already determined, and then I equals vertex of I minus 1 over m, and then 0. Everything is the same. Then we used up m times n plus m plus 1 point, meaning mn plus m plus 1 point, meaning m n plus 1 plus 2 points. Now everything is clear. Phew, we completely correct the problem. So lowercase m and n represent the interior points in each direction, right? In this direction, there are m interior points. In the other direction, lowercase n interior points. So somehow I was confused, but now everything is corrected. So from this point on, we will not have any trouble like this. Then the next, now vertical one should be determined. So let's determine the vertical one. Then because these many points are determined, you can use the same line, but let's do it for I running from 1 to now m n 1 to n. Because our 1 pointer is already assigned, we will start at this point. Instead, we initially started at the left-hand side point to the right-hand side point. But because this point already has index, we will start at this point, right? So we will do the thing here. Vertex of m multiplied by n plus 1 plus 2. This is R used, right? Plus now I, right? Plus now I equals 0. This direction is 1, right? X coordinate is 1. And then y coordinate is I over n, right? Or j might be okay because we use the j index in this direction, right? So you can change it. So please check whether you understand this part or not.
What is that part from?
The right-hand side. We are covering the right-hand side of the domain. Going up, right?
One above that, no, the bottom now.
boundary like this. We are covering the boundary. We covered initially this boundary. We covered this boundary by the first loop. Now we are finding this boundary. This boundary. These boundaries. So if you have a question, ask me. Then how many points were used up to this point? We used all the numbers like this. n plus 1 plus 2 plus total n numbers, right? Total n numbers. Or we can write it this way. n plus 1 plus 2 plus n plus 1. And then n plus 1 and n plus 1 are common, right? This is the common factor, so we can factor it, and then 2. So these many numbers were used to cover these two boundaries. So next time, we will use this. Any questions? Just a simple arithmetic, right? Uppercase n is the same as this. So uppercase n is the common factor, and then n plus 1 is used, and then 2 is used.
So that's all the interior plus those two boundaries?
Right. All interior has mn num points, right? And then this has n plus 1 points, and then this has n points. So if you add all these, then these many points were determined. All the interior points are lowercase m times n points, and then n plus 1 points, and then n points. And then here, m points, right? Here we will cover m points, right? We will cover m points. And then finally we will cover n minus 1 points, n minus 1 points. So n minus 2 points. There are n minus 2 points, right? Because we covered this point already and this point already, so we have 2 less than this side. 1 less or 2 less? 1 less. 1 less. N minus 1, right? So we will cover this kind of case. So m plus 1 point covered, n points covered, and then m points covered. Now we covered this point and this point. So we have 1 missing here, and then 1 less than this one. So n minus 1 covered. Then total, how many points are covered in the boundary? How many points are covered in the boundary? This plus this plus this plus this. Total how many? 2m plus 2n. Do you follow me? Is it reasonable? 2m plus n points were covered in the boundary. So let's write the routine assigning these points. Then for I running from 1 to uppercase m, right? Uppercase m. Vertex of m plus 1 multiplied by n plus 1 plus 2, now plus I, right? Now offset equals y height is determined. Y height is always 1. And then we are subtracting from m, right? We are subtracting from m. So subtract this number, right? From m, we are going back. m minus 1, m minus 2, m minus 3, m minus 4, and so on. We are going back. So I am covering the upper boundary points. And if you don't follow me, ask me. No problem? Do you understand the reason why I used m minus 1, m minus I, or not? So these are upper boundary points we want to cover, right? These are upper boundary. So first, when I is equal to 1, we want to cover this point. What is this point? Here, right? So m minus 1 over m is this point, right? And then m minus 2i, right? m minus 3, m minus 4, right? So we are covering these points by using this. And then finally, we should cover the boundary here, right? We should cover this boundary. So before going further, let's add all the numbers used. M plus 1 point, N plus 1 point, plus 2, and then I runs from 1 to M. M points, and then M is nothing but lowercase m plus 1. So we have m plus 1 and m plus 1. So m plus 1, and then n plus 2 points were used. So we used these many points. So the next one is like this. For j running from 1 to n minus 1, right? There are a total n minus 1 point remaining. Vertex of this much, these many points, right? Plus j, position equals, now the x coordinate is fixed, x coordinate is 0. And then y coordinate reduces, right? So this way we can completely assign the points when m and n are given. So give me on m and n pair. So like 100 here, 50 here. Then once we know the number of sub-universe in each direction, then automatically this will fill the vertex positions. So now, once I, for instance, say vertex of 5, vertex of 73, then it will give us 5 tenths, 5 tenths. Right? It will give us this result. And then now I say, oh, vertex of 78, then it will give us 6 tenths and 5 tenths. Right? So vertex is given, and assume that I give, of course, we are assuming that m is 10, and then n is 10. We are assuming this thing, and then, for instance, if I say vertex of 82, then it will give us 0, 0. Because of our design. So automatically, all the correct positions are calculated. But as I mentioned before, this is not the only way to assign vertex numbers for each position. You may design something more brilliant than this one. So let's pause, and then, unless you have questions, the next step is finding the linked points. Usually, in our case, we can find the linked point like this. Even when you have boundary, we don't care. Like east side point, right? East side, northeast side point, and then north side point, west point, southwest point, south point, right? These form a boundary, right? These 6 points form a boundary. So there are 6 surrounding points. So it's like this. Vertex 1 has these 6 points, right? These 6 points. But instead of using point coordinates, we are using vertex number. For instance, assume that we have 37th point here. Then the east side point is, here I wrote down east side point. So I will label this differently. Vertex is purely xy coordinates, so I will say link information. Link information. First vertex has link information 1. Link information 1 is this. We have the first index, then second index is 2, right? Do you follow me or not? The east side point is 2. If our vertex is 1, then our east point is, and then northeast, north and west, southwest, and then south. So we need to determine this thing. So we found this thing, and then northeast point is like 1, 2, 3, 4, 9, 10, 11. 11. and then 10. Any questions? And the west side point is the last point, 121. Southwest point is the 00.82, and then 83. So this is the link information surrounding the given point. So if you follow me, it is good. If you don't follow me, ask me. But before going any further, I will write down the situation. This is the first position. This is second position, third position, and so on, and so on. And then this is the 10th position, 11th position, and so on. And we go all the way. And then afterwards, we cover 82, 83. And we go all the way, and we arrive at this at 121. So this is the situation. And it's clearer, right? You have surrounding points like this. So I am writing the link information of the first in the node, right? First node has this link information. Assume that you have more than 6 triangles involved, then we can add more link information here. If you have a question, ask me. If you don't, then I will continue. Then let's find the second link information. So please find second link information on your own. So assume that you have a point right here, and find the second link information. What is the east point? If you don't understand, you may ask me. So we now create the link information. In other words, we use vertex information and link information in our code. Vertex information and link information will be used to define everything. We are almost there. Once we mix these things together, then with basis function creation and solving, we can finish it. So we have these kind of things. And then we may need this kind of point. What is the link information of 83? 83 point. Point 83 should have link information. What kind of link information? East point is 84. And then northeast point is 2. North is 1. And then west point is 82, and then missing, right? Missing. M is misleading, so I will say missing, right? Missing, right? Do you follow me? So 0.83 doesn't have southwest point or south point. Then how can you design it? In this design, what number would you assign here? If you were the designer? 0, 0. So it's my design, but I decide to use 0, 0. In other words, if you have any miss, then 0, 0 is assigned. And later, when we read the code and the code information is 0, then you know that there is no triangle in this direction. Then you can ignore and then go to the next triangle. And in other words, we should cover 6 triangles usually. We should cover 6 triangles, right? First, second, third, fourth, fifth, sixth, right? But once we have any miss like this, then we go to the next triangle. So we are running for 6 triangles. But each time when you see 0 link, then it means there is nothing. 0 is nothing, and then we can. Then please find this one. L of 2, L of 1, 2, 1. Please find L of 1, 2, 1. Oh, this is the last one, right? This is exactly the last one. So please find it. What is L of 1 to 1? Link information of 1 to 1 is what? East side is. So please find these things. So link information of 1 to 1. East side is what? And the north side is what? And so on. Do you follow me? So east side is 1, northeast side is 10, north side is 1 less than this number, that is 120, and west side there is none, southwest there is none, south side has 82. Finally, please find link information of 82. Link information of 82 is what? So 82nd nodes have link information. So please find, right? Please find this second link information of 82. 82 has link information. '83, 1, 121, 0, 0, 0. So we now have the link information of every point. In other words, in our design, we had node information. Once we say V of something, V of 37, then it means a specific point position, right? Now, in addition to that, I say L of 37, then it will give us the information, and I will show you how it runs. So you may pick, you may pick your own point, then I will show. So I will make a break at this point. I will make a break at this point and then show you. Then now we create the link information, right? Link information I calculate this way. East side direction, northeast side direction, north side direction, west direction, southwest direction, and south direction. So now let's look at the matrix or something. So for instance, are you interested in a link of 37? How can I get, I guess link information has two-dimensional vector, so I should write this thing, link information of 37, and then this. So this is the link information of 37th point. 37th point has right side, east side, northeast side, north side, and then west side, and then southwest side, and then right south side. I guess 37th point is not 5, 5. Let's check 37th point. Vertex K. What do you think is the problem here?
Vertex only has one point.
Oh, really?
Was it?
Let me,
That should be twice.
I do not understand. Vertex. I do not understand what is happening. Let's go to the workspace to look at vertex matrix. V means something different. Did I use V? I do not know why this happened. Vertex. It's really strange. But in any case, let's not worry about the details, but just to look at, focus on the problem. First point has these surrounding points, right? First point. And then second point has these surrounding points. And for instance, 82nd point has these surrounding, right? 82nd. So it doesn't have any west or southwest or south. 82nd point is 0, 0 point. Quite the opposite point is the upper right-hand side corner points. Do you guess the position number? Let's not try. And in any case, these are the things done. So if you have a question, ask me. Then the next thing is this one. Do we have to really populate these things manually? Do you really have to populate these things manually? I did. So what I did was creation of finding the vertex index, finding the index of the vertex using a function. So assume that xy coordinates are given. So this is what I've created. Find the vertex function I created. Find the vertex function is this one. For instance, 0.5, 0.5 is given. Right? Assume that 0.5 is given. Then can you find the vertex point? That kind of thing. That should be created. It's not very difficult to create it. So I will show you. I'm not saying this, mine is the best one, but just I'm trying all the possible ways to solve the problem. So this is the program that I designed. How did I find the vertex? Of course, we need uppercase M information, uppercase N information, but instead of sending uppercase M and uppercase N, I used lowercase m and lowercase n and the vertex information plugged in, and point goes in. So I plug in M and vertex information with point information. Then what it does is this one. It checks the norm between the vertex position and the point, and if it's small enough, such as 1 over m plus 1, is small enough, then that index represents the vertex position. So roughly, simple program does the work. So I found these things, found the surrounding 6 points by calling this find vertex function many times. Then the only thing that I need to do is changing the position. Initially, we had the given vertex. Then now I go to the east side direction, and then north, east side direction, and so on. And then for each point, we call the find the vertex index function to get the integer representing the point. So this is what I did, and I will show you the color. I call this thing like this. I call this thing like this. I define east direction, right? This is the east direction. From the given point, neighborhood triangle east direction is going dx amount, right, in the x direction. What is northeast? Going dx in the x direction and then dy in the y direction, so dx and dy. So this is the northeast, right? Similarly, northeast dy addition, direction west is adding negative dx, southwest subtracting, and so on. So I created these 6 vectors. 6 vectors were created. And then I find the vertex number for each direction. So vertex plus east is called, and then that is stored in the first position of the link, right? First position of the link vector. And then second position of the link vector, third, and so on. So link vector of 6 entries were filled by these things. In other words, we are finding all the entry, all the related surrounding points. Then this way, we create the vertex information and the link information like this. Let's call one more time link information. Link of, for instance, what is good? Like 33. Then it, so it gets link information. 33 position has east side 34, northeast, north side 42, west 32, and so on, right? So did I really populate these things manually? No, I just called the program. Find the vertex number, and then. So essentially, we completely populated vertex matrix and link matrix, and let's take a break and then resume at 3:05 by this clock, or 3:07 by this clock. Point is 5.5 points. So let's examine. 1, 1 is the first, right? First point is 1, 1. Second point is 2, 1, 0.21, I mean. And then 0.3, 0.1, 0.441, and then 0.1, 0.1. This is 9 point. And then now 10th point goes up, right? 10th point goes up. So 1, and then now 0.2, and 18th point is 0.9 and 0.2, right? And then 27th point is 0.9 and 0.3, and then 36th point is 0.9 and 0.4 I mean. And then 37th point is 0.1 and 0.5. So I made a mistake when I hand calculated. And as you can see, once we program, it will easily create this kind of list. And then we can follow this. And then as you can see, 41 point, right? 41st point is 0.5, 0.5. And then we can continue. And then 81st point is 0.9, 0.9. 81st point. First point is 0.9 point. Do you follow me about the interior points? So as I mentioned, first point means 0.1, 0.1. In other words, in our program, we don't really use actual coordinates. We don't really use numbers in the domain. We are using indices, right? So we should know what index means, what point. So for instance, 38 or 81 is not the actual number that you should use to calculate the value of something. 81 just represents the point. 81 is like 0.9, 0.9. And then afterwards, you return back to the boundary, and then 0, 0.8 second point, and so on. And then we completely created this thing. And then we go all the way to the right-hand side, and then we go up. We go up, and then we go to the left-hand side, right? After going all the way up, we go to the left-hand side. We go to the left-hand side, and then we go to the left-hand side, we go down. Then we completely fill the, so I showed you the vertex assignment. Any questions about vertex assignment? Can you really program? So vertex is created this way. But technically, you should use this kind of command in MATLAB. In Maple, there might be a better way. But technically, you should assign this kind of thing. This is the technique. I gave you this formula, I plus j minus 1 times m, right? And then this represents all possible things in the vector, right? All these things come in to one position. In other words, you should not say, oh, something I, j on the right-hand side. Just everything is in the one position. And then we collect these things in this wild card. And the link is also mentioned. And then let's see the link. This represents the link table. 6 points link, right? Assume that you are really programmed randomly generated stuffs, then you don't necessarily have to use east or northeast or something. Just from anything from the horizontal line, you search the neighborhood point counterclockwise and then locate the link position in the vector. But we may need more columns than just 6. We may have more. But 360 degrees mean about 6 regular triangles, right? So about 6 might be optimal. But sometimes it may have like 10 triangles, but it's very rare. 10 triangle means we are using very bad triangles. Best triangle is the regular triangle, right? Best triangle is the regular triangle. So you don't have to use too thin triangle or too thick triangle. You don't have to use that. But in any case, you create this kind of thing. Assume that you are allowing like at each point like maximum 12 triangles, 12 surrounding neighborhood triangles, then you can add more columns here, right? And then instead of just searching north or northeast or so east or something, just you go from the horizontal line and you just rotate one circle to find all the closest surrounding points. And then we assign this kind. So design-wise the same, right? Design-wise the same. So for instance, 22nd point has east, northeast, and so on. As you can see, sometimes you see 0. You see 0. By the way, I will explain the reason why I used norm there. I saw zeros here, right? Why? Because this is the boundary point. So once you have boundary points, we have a lot of zeros. Boundary points have a lot of zeros. So do you completely get the idea? And the technical part. When I initially tried to just match this thing, somehow a strange bug happened. So let's go to the program part to see it. When I created this thing without this thing, in other words, I just tried to match the j's vector, j's vertex and point. In other words, I used equal, but somehow in computer storing system, even though I meant the same point, it doesn't match. They do not match. They do not match. So they said 2 points are different, even though I meant the same points. When I used equal, so you should try to avoid equals in computer program, because equals is very delicate, especially when we handle the point using like a floating point representation that we learned. Because of that kind of reason, it's good to use norm instead of just exact match. So you should see the reason. In other words, I could have programmed this differently. In other words, if norm, if vertex j and points are the same, I could have programmed this way. Then strange malfunction may happen. In fact, it happened to me. So I didn't understand and went to the debugger and it didn't hit, even though I gave the same point. In other words, vertex j is 1, 1, for instance, 0.5, and I used point equal to 0.5, and then I ran, but it doesn't hit. Why? Because somehow, the floating point handling might cause some kind of delicate difference. So instead of using equals directly, I used the norm. In other words, the vector norm means the vector distance difference. Any questions? Then almost there. We are almost there. I will show you how many more lines are necessary. So take a look. Once you look at, you will get the idea. Initial design is almost second thing. We came all the way up to this link point, right? And then as you can see, from this point on, we determine A matrix, right? A matrix, and then we determine B matrix. We determine B matrix, right? That's it. And then we determine C matrix. C matrix is a coefficient matrix that we want to find, right? Because by FEM, we already have basis function. Then once we determine C, we are done, right? Because basis function multiplied by C will give us the result. So all you want is determination of C. So to determine C, we need the A matrix and then B column vector, right? A matrix and B column vector, and then we determine C matrix. This is the remaining. So let's briefly return back to the theory part. So we are almost there. So take a look. We initially design this way. We assume that solution is basis function times C, right? Sum of basis function times C. So once we determine C, we are done. Because basis function has nothing to do with any differential equation. Basis function is determined by just our design. So determination of C is everything. So let's go down. And then how do we determine C? Roughly, this is the determination of C. We solve this system, then we are done. Right? We solve this system, then we are done. Then to solve for C, we need to determine A matrix and then B column vector. So we should determine A and then B. Then by solving this system, we can determine K. So this is all I did. As you can see, I did this, right? I created A matrix consisting of small entries, and then I determined B, and then I calculated, and then I call this thing, right? So if you have a question, ask me. If you don't, then I will begin to cover the details of secret part, A matrix determination, and then B. Then everything, the only remaining thing is just assignment. It is very unfortunate. MATLAB should include magnification. So if you know MATLAB people, email them. If you don't magnify, we will boycott. Because we couldn't see it. But Maple or others, we can see. So please change. So roughly, this is the remaining. So almost there. We are almost there. Then let's do it. To calculate A matrix, all we need to do is this thing. Just this calculation for each surrounding triangle. Because if it's not in the triangle, surrounding triangle, the calculation will give us 0. So because all other triangles have 0 value of the 0 integral value, all we need to add is the integral of this surrounding 6 triangle, or possibly 6 or less than 6 triangle, right? So we integrate over these 6 triangles. That's all we need to do. Any questions? Then let's go to the program part. So how I did it? It's very simple. So as you can see, I run these things for, initially I fill the A matrix with zeros, right? A matrix has 0, 0 everywhere. And do you now see the mismatch between row numbers and column numbers? Why? Because A matrix is symmetric. A matrix is symmetric. We don't have to store everything. We need to store, as I sketched before, A matrix looks like A matrix includes these parts, and then this is used for B, but you still store these things. And then this is the copy, symmetric copy of this. So I explained these things before. So this is the reason why I designed the matrix of m by m times n rows, and then m plus 2 times m plus 2 columns. Because it's symmetric. We don't have to store any further. In other words, if we calculate A11, A12, and so on, and A22, and so on, A33, and so on, A44, and so on, then we are done. So all we need to do is the calculation of Aij, doing the integration. Any questions? And the integral here is not very difficult. As you can see, integral here is nothing but integral here. Integral here. A combination of these two, if they are the same, right? If they have a match, if there is a match between I and j are the same, if I and j are the same, then we use top one. If I and j are different, we use the bottom one. That's it. This is all we need to do. Any questions? Then let's do it. We integrate over 6 triangles, and then I'm showing you 6 triangles. Then, as you can see, we initially fill these things with zeros, right? We fill this matrix with zeros. And now, I will do the integral for each position. I will do the integral for each position. In other words, one function does all those integrals to fill these matrices. So just one function is called each time. In other words, I determine the position, k column position, k row position, right? So I just pick k column and k row position, right? Then it calls the function doing the integral. So I create the function doing the integral. Do you follow me or not? Then let's go to that part. That's the final part. Then essentially with that, we populate a matrix, right? We populate a matrix. So you should understand the goal. Our goal is the creation of a matrix, and then B matrix or B column vector, and then solve this system for C, and then using C, we solve the problem. So this is the remaining part. And then to populate A, what I do is just one function. Just this function does the integral. So I will completely analyze this function together. First of all, when the indices kr, k something comes, then it knows the node, right? So as you can see, take a look. So once this position comes, right? Once this position comes, then we know the surrounding points. So we know the surrounding point, and if these are not surrounding, in other words, if we hit the boundary, we don't return anything. And then we should integrate them, means we should sum. So where do we have? So I will add the integral of this first triangle, and the integral of the second triangle, integral of the third triangle, and fourth triangle in val value, right? So val value has the sum of the integral in each triangle. There are 6 possible integrals, right? So val has the integral value. So initially val has 0. Now we first check the first triangle. If it's a legitimate first triangle, then we do the integration. We do the integration and then do the calculation and then add to the value, right? Add to the value. So depending on the number of, in other words, the node match, then we should use this formula. If node number match, if the node number match, then we should use this formula. So I used it, right? I used I don't know this name. Computer. Do you know why this is happening? Bad computer, right? In any case, this is the idea. So we go in with I index and j index. These I and j indices represent the vertex number. In other words, vertex 5 node, vertex 2 node comes in, right? Then that means P1 and then P5, right? Vertex 1, P1 and then P5 multiply together, and then we are integrating. So let's return back to the program to indicate the idea. Because they are the same, then we should use this formula. If they are different, then you should use this formula. So depending on the condition, this or that. That's it. And then we do this thing for each triangle. First, east side triangle, and then northeast side triangle, and so on. North triangle, and so on. So we do these things for 6 triangles. And then we add the integral values of each triangle. If we have zero link information, then we skip. We just continue. So we rotate 6 triangles for each JK. So I will go to that part and then finish it. But what is happening? I guess it might be MATLAB error. MATLAB uses licenses and checks license, and if somehow network is gone, then returns back. So take a look. So I will now explain line by line. First of all, value is the integral result stored there, right? Initially, value has nothing. Now, this is the, so I will explain with the, so it's like this. Phi, I want to explain exactly the same, KP and JP. Why did I use KP and JP? KP of x, JP of x, gradient, right? Gradient, dot product of this gradient, integral t. So this is all I want to do, right? This is all I want to do. So, thank you. JP. Right? So this is all I want to do. And then this determines ij position, right? Ij position. By definition, because we defined this way. When you defined ijk, we defined this way. But this definition doesn't just ask us to integrate over one triangle. It asks us to integrate over the whole domain. That's the reason why we are integrating over the surrounding 6 triangles, because outside these surrounding 6 triangles, the integral value will be 0. So all we need to do is the 6 triangle integration. Do you follow me? Then, as you can see, what I did was this one. We have the input node values, right? So we use the link information. Once KP is coming in, we have the neighborhood information, right? KP position, KP vertex comes in, then we want to check 6 surrounding nodes. To do it, what should we do? Link of 6 position, right? I mean, link of this JP position. So I add the vector, keeping the node information, right? Node information. Do you follow me or not? But to make a cycle, I added one more, right? I used this technique over and over again, right? To make a cycle, I made 7th one. This way I can easily program stuff. Any questions up to this point? In other words, once Aij comes in or Ajk comes in, we check surrounding node according to the first one, right? First index. Then we found the 6 surrounding nodes. And then if these 2 numbers are the same, if these 2 numbers are the same, then what formula should we use? If 2 numbers are the same, then we should use this formula. So I have this branching, right? The same or not, right? Two cases remain, right? Same or not. If they are the same, then for surrounding 6 triangles, I do the calculation like this. I do the calculation like this. x2, y3, y2, y3 are programmed by just node information. It's not very difficult to do it. And in fact, even this one is, I create one more function doing it, but roughly I'm just giving you the outline and then later return back to show you individual function. But as you can see, we should check whether link information has 0 or not. In other words, if link information is 0, we don't have any triangle in the direction. In other words, that kind of integral doesn't even exist. So if somehow this happens, we continue. In other words, we ignore that triangle part. Out of 6, 1 is ignored, right? The same thing, right? If it's not a triangle, then we ignore. So we are integrating at most 6 triangles, right? Over 6 triangles. But if link information gives us 0, then it means it's not a triangle. So we just omit and then other thing. So roughly this is the design other than the detail. But if you have a question up to this point, ask me. So I'm showing you the design, modular designs. We just design from the top and then we go down, and the details are not very important. Just it's very trivial in some sense. So please look at the idea and ask me. So doing this determines all jk that I mentioned, right? These whole matrix is determined, right? So assume that we pick some point, right? We pick some point in the matrix, then we can find it by just doing this integral using this idea. So I said integral phi11, integral phi12, right? Integral here phi11, right? Phi11 or phi12. I created 2 functions.
How does the x sub 2, x sub 3 on that?
So those things will be explained. Yeah, but let's not worry about the details, but worry about the structure. In other words, how do we determine coefficient matrix or Aij matrix? We do this. Then now it's time to go to details. So you now completely understand the idea. Initially value is 0. We collect the node information. I do not know why I use NB, no neighborhood, right? NB, neighborhood, neighbor, right? NB. That's the reason I used. And then KP, KJ, different formula, right? 1, 1 formula. If they are different, 1, 2 formula, right? That's it. Essentially, this is it. And then we do the bookkeeping. If we have non-triangle or it is boundary, then we don't integrate, just continue. And then when we have matching nodes like this, then we can use this idea. But if we don't have a match, then we don't even have to do it, right? Because we are, for instance, P1 is here, P5 is here, then there is no chance of having common area to integrate. If essentially 0, 0, right? Everywhere is 0. So to do it, this node should be one of the surrounding neighbor, right? Do you follow me? We have phi j, phi k, right? Phi j and phi k. If they are far away, far apart, then there is no chance to have dot product positive or dot product non-zero. So they should be close. How do I check? I check this way. Neighborhood is JP. Right? There are possible 3 points. Point itself, right? Vertex itself, or east, or the first node in the triangle, or second. There are 3 possible points. So first one is checked upstairs. First node is checked upstairs. Because there are 2 indices coming in. First node is checked. If they are the same, then this happens. If they are not the same, the possibilities are, this could be the same as the second node or third node, right? There are possibly 3 nodes. If all of this value means they are far apart. In other words, 0. In other words, 0. So roughly, I explained all the necessary stuff other than the detail. And then after this step, I will go to the details and then explain the idea. Any questions? Then integral. As you can see, we need to do this integral. Then this integral involves this kind of calculation, right? This kind of calculation. And then this integral involves this kind of calculation. So all I did was creation of these things with vertex information given in, right? As you can see, vertex information is given. Let's go to the integral first on one. It's very simple. So we have the triangle coming in, right? We make a triangle coming in because we are integrating over each triangle, right? We are integrating over each triangle. Triangle information should come in. Then right. 3 vertices, like 0, 0, 1, 0, 0. So 3 vertices information coming in. Then we're using these things. I calculated this value. I did a little bit technical linear algebra stuff, but you can make it primitive if you want. It's completely up to you. So always I enter the triangle information. So let's return back to the color. So as you can see, first point, this is the first point. Do you follow me? First point, right? KP is the first point of the triangle. So we are integrating over each triangle for 6 times, right? Let's write it. We are integrating over 6 triangles. So first triangle first. First node, second node, and the third node, right? So we are integrating over this triangle. So what I did was inputting these 3 points to the integral 1, 1 in case that KP and JP are the same, right? K and J are the same. So once K and J are the same, we just input 3 triangle information. Then automatically this formula kicks in, right? This formula kicks in and solve the problem. This right-hand side formula when these numbers match, these 2 numbers match. So this is what I did, right? So what I did was sending the point information, first point coming from this KP, right? And then second point coming from this 6 possible combination, right? First triangle first. So first triangle first. And then next node, right? Right? So first node and the next node. So we made a triangle. And then we do the integral of this thing and then add. And then now, because K changes, it's the second triangle. And then do this. The vertex itself does not change. So always this does not change. But these things change for 6 possible triangles. Then we are done. Then the only remaining thing is this. You handle 6 points, 3 points coming in. Right? You know, 3 points are coming in. Then, in this program, 3 points are coming in, 0, 0 coming in. Then this is x1, This is y1, right? This is x2. This is y2, and so, right? x3, y3. So using these things, we can just make a formula, right? So this way, as you questions, we handle x, y, z stuff. So essentially, we completely handle for 1 case. 2 case is exactly the same. Let's not worry too much. Just look at the program. So just different format. Essentially the same design. Then it means after this, we now know AKJ, right? AKJ is completely determined by the color, right? So AKJ is called. In other words, we now populated the whole matrix. I will pause and then you can check whether you completely understand this.
All of the triangles are the same shape and size. Will that determinant always have the same value?
Vertex position changes, right? Vertex position changes.
But you're just either translating or rotating.
In fact, we designed these things uniformly. There couldn't be much difference in reality. Once you see these things, you will know that your guess is correct. So did I store these things somewhere? Did I make a break somewhere? Not necessarily. So let's run these things and then look at the AKJ part is completely populated after this. So let's make...
You were computing the determinant each time you called one of the
Right. So I will do this FEM 5, 5, 5, 5, 5, 4, 5, 4, 4 might be good enough. So I will run it, and then I take a break, then I will check the shape of AA. There you have many numbers similar. So as you can see, as you guessed, the matrix that I represented here, right? The matrix that I represent here has actual values. So take a look. Have you guessed? But I didn't even care. Once I programmed, I didn't even look at these things. So they couldn't be very different because we uniformly divided and then integrate same way. But why did I mention this? Because in real world, we may have not uniform partition, right? We may have arbitrary partition. Then these things will change. So please browse the idea and ask questions. So now I completely populated AKJ. So I will pause, and then you may check whether you completely understand everything up to this point or not. You completely understand everything up to this point. In other words, I will show you. I created vertex, right? I created vertex, and then I created the left, right side, and boundary, everything. So vertex is completely created right here. And then after creating the vertex, I create the link information by using 6 different directions, right? And then after creating vertex and link, I now populated Aij. The only remaining thing is Bij, right? Then we can solve it to find C. Then after some bookkeeping, we are done. So I will pause, and then you can check whether you completely understand everything up to this point or not. Then B is nothing but just sum of what? B is nothing but because G is 0. Even though G is not 0, we can do it. But because G is 0, B is nothing but CK with these things, right? CK with these things. But CK runs from boundary, not interior. In other words, boundaries from, the index runs from outside the interior, right? Outside interior. So in other words, all the involved terms are 82nd term, right? Up to 81st term is interior. So 82, 83, up to 121. Those numbers are all added here. But we calculated Aij even for those boundaries by our calculation. We've already populated even unnecessary part. So Aij is completely known no matter what. What I do is now populating B column vector. So all we need to do is, because G is 0, all we need to do is finding CK and multiplying CK, and this is AKJ, right? So multiplying CK and AKJ to determine BJ, and then summing, right, with minus. This is all we need to do. Any questions? Then how can you find CKJ for the boundary? Use boundary conditions. In other words, once we have this boundary, then use this boundary condition for the 0, 0. Then 0, 0 value gives us something. And then 0.10 gives us something. So we collected this information, collected this height information at boundary using. So it's straightforward. How I did it, I'll show you. This is what I did. So I created the boundary function like ux0, uxm boundary, right? x0 boundary, x0 boundary, xm boundary, y0 boundary, yn boundary. So I created boundary functions here. So I intentionally changed the boundary condition from the one that you have. But I made up some boundary conditions on my own. And then after boundary functions are defined, I just call the boundary function like this with appropriate point information that I introduced. So do you remember the point information? For instance, left boundary, then I said vertex of something equals. Use the same idea as that one to determine C. So I determined the C like this, right? Do you remember this thing? You saw this thing before, right? Bottom boundary had this kind of thing. Do you remember it or not? So we started at, because m times n interior points were all determined, we now run from 1 through capital M plus 1 or lowercase m plus 2. Then this goes through the bottom line, y0 line, right? And so, right? So we do these kind of things and then determine C for every number. So we determine C for every number, every boundary numbers. So we determine the C for every boundary number. And then now B is nothing but the sum of these kind of things, right? Sum of CKJ and then AKKJ, right? So I just changed the J by KJ, right? In the formula. In the formula I had J, BJ. I had J, right? But instead of using J, I used BKJ, right? KJ. So KJ was used here. So what I did was using KJ. And then we sum these things and later minus sum. So what I did was just do this calculation. After determining the boundary C case, I just multiply each thing and then add this thing to K. Then now we are almost home because we now determine everything. Then we can solve this for C. So what I did was solving this for C right here. Solving this for C. So I called it X. Then final thing is the assembly part. Final thing is the assembly part. After solving this for C, we now have boundaries and interior together. So all I did was just a linear combination. Linear combination of C matrix having these kind of things. In other words, we have, this is too technical. Let's not worry about technical steps. Let's not worry. So roughly, you are there after finding C, just you can use manual thing or anything you want. Then you can, but because you already created the basis function, all you need to do is multiplying. All you need to do is multiplying CK and then phi k that you created, and then summing these things from 1 to 121. And this is the solution, right? All you need to do this. Because CA for the interior were found by solving the system. CK boundary were found by boundary conditions. So just by mixing these things technically or manual, any way you want, then you can find the solution. So this is it. Roughly, we completely finished all the necessary steps. And I don't want to cover too much, so I will not cover any new material other than the stuffs you may ask. You may ask something, then even if I didn't cover this before, I will mention.
Did your FEM function plot?
No, you don't have to plot. Let me briefly return back to the problem itself, because if I asked you, I should not change it. No, I didn't say it, right? But plotting is nothing. I will show you. I used the linear combination command to plot, and the linear combination command is called final, right? This is nothing. Linear combination is called, and the linear combination has plotting. Once the linear combination is called, then all it does is like creating this part. What I did was this one. I divide x direction by 100 subuniverse, y direction by 100 subuniverse, and then I calculate the value at individual point inside the subuniverse, and then stored it in phi value matrix. And then I surface with this. Just like what I did was, because I don't know very much about MATLAB, I just do whatever it works. So roughly all you need to do is just creating x directional mesh, y directional mesh, and then in each mesh we calculate the phi value, and then we surface x, y, and then phi value surface. This part is not necessary. All you need to do is the point up to this. All you need to do is the combination, right? Linear combination. So technically what I did was this one. Interior points were interior point related coefficients were from this X matrix that we solved, right? So this gave interior. And then now, in addition to C, I attach more points. I attach more points. If you follow this, you won't get anything meaningful, because that C and mixing was for my scheme. It's not for yours. So up to this point is the one you can use. But because I designed this way, what I did was this one. When I call basis functions, I used this kind of scheme. So I will run it and then show you. stop? Where is the stop? Exit debug mode. So let's close everything. So I will show you the reason. So this doesn't work with your design, but with my design, I need to input a certain way. My input idea is this. I input the value of m sub-universe and then n sub-universe. So for instance, 10, 10. These things are going in. Afterwards, what I did was, as you can see, what I did was linear combination, getting the coefficient matrix. Coefficient matrix. How? I wanted this kind of thing. Usually solution looks like this, right? Solution looks like this. And then what I wanted is this one. Because this is obvious, this is obvious. All I want is CK value and then this K index together. This kind of pair, right? And then that, so I wanted this kind of thing. More precisely, for instance, C1 is like 5, and then first phi1 function, right? 5 times phi1 function, and then 2 times phi2 function, and then 1 times phi3 function, and then 4 times phi4 function. So I designed this way when I designed the linear combination. So what I need to do was storing the C information with phi, matching phi subscript or phi index. So 5 times phi1, 2 times phi2, and so. So all I did was just attaching these kind of things, here, right? So second entry now has index from 1 through the last one, right? 1 through 121. Because I store the C in just one dimensional vector. Right? One dimensional vector has C value. C1 through C interior. C boundary was calculated by boundary conditions. So now I have C boundaries. But my design asks the matching subscript in the phi function. So I just added these kind of things in the second column and then made a linear combination like this. So as I mentioned, this part is not for yours. This part is not for yours. It's not for mine. So up to this point is the one you need. So you may ask any questions about any part of this program or even design of the program. And please check your notes and then check whether you can do these things or not.
Are you only evaluating the solution of grid points? To make any kind of solution, or because we are integrating stuffs, we essentially do not need, as you can see in theory, we don't evaluate values at all. In some sense, integral is very like a global instead of local. Global isn't a very good word. It does not depend on xy position. It depends only on triangles. In other words, when you calculate these C's, C doesn't know whether it's x or y. It only checks about the number of sub-universe, uppercase M and uppercase N. But other than these M and N, frankly, these things do not care. It doesn't matter. But when you create the basis function, then xy position matters. But to solve this thing, we don't have to worry about x, y. That's the reason why you didn't need these steps in this consideration, even though design looked similar. Because last time I showed you the method of designing these things, right? But these are similar, but there we worried about this kind of x, y position. So we need to know how to subdivide, right? How to divide or how to create meshes. But here we don't have anything like this. All these are just quantities depending on just triangles. So in this sense, we don't have to worry about meshing or something. But in any case, it depends on m and n, right? You have m position and n, but it depends on m and n.
Right. I guess what I'm saying is we've solved this system.
Yeah.
And now we have a vector of your C value.
Right.
And those are the coefficients of a linear combination
Right.
of basis functions.
Right.
And now we want to evaluate.
So that's the reason why I'm explaining this. In other words, C calculation has no concern about xy position, but basis function contains it. In other words, basis function checks xy position.
That's right.
Right.
But my question is, now we have this vector of C value.
Right.
And now we want to see what the solution looks like.
That's the reason why the linear combination of.
That's right.
Right. So what your question is the question about this kind of linear combination. But as I mentioned, this was already completely created, right? This was already created. So it's not today's problem. It's last week's problem. This is last week's problem.
Well, that's right. But what I'm saying is, if we are only interested in the solution at, say, grid points, it's easy to evaluate the basis functions at those points.
Right.
It's all one,
Right.
right?
Or,
The basis functions are.
but it cannot be up node. In other words, it could be some interior points, not the node points.
Right.
So assume that what you want to find is the node point, then there is no problem. For instance, we want to,
It's just a corresponding C value.
right, corresponding C value will do it, but assume that we have, so assume that these are nodes, right? Assume that these are nodes, but assume that we want to find this value. Then without basis function, how can you find it?
That's right.
Yeah.
That's right. But if you just want to know the solution
Then right, it's easy. But assume that we want to find the value at this point, then without the basis function, we don't know. So that's the reason I separated two problems. In other words, we need basis functions to find this kind of value. Assume that we are asked to find values at these points, then there is no problem. But assume that we are asked to find the value at this point, then without basis function, we cannot do it. So your question was about just using node, but my answer is we completely separate these things. We completely separate the basis function and the C determination. C is determined at the nodes. But once C is determined, then by linear combination, we can find the values like this at any point in the given domain. Any point. Give me any point. So assume that we have node here, but give me a point here, around here. Then what is the height? Because we designed our basis function, the value here can be found without really more dividing these things. Other questions? So roughly we covered the steps, and in fact already some students submit the final and number A, homework A. But if you still have difficulties, let me know. So I separated these things completely, and as I mentioned, basis function has nothing to do with any differential equation. Just divide using node and link, then you will find just the basis functions no matter what. Now we mix these things with differential equation solving. To do these things, we need A coefficient, right? Aij or Ajk, and then Bj, and then we create the system and then solve the system to determine C. Now we use this C to the in the basis function that we created, then we have linear combination of basis function covering the whole surface. Then even though we have off node points, because of the basis function, we can find the value. We don't have to divide more to resolve these things and then return back to the point. Assume that square root 2 is given. Then how can you subdivide square root of 2? It's impossible, right? No matter how refined the mesh you use, square root of 2 is missed, or 1 over square root of 2 is missed. Then no matter how small subinterval you use, you cannot really hit it. But in our case, we don't have to worry. We just divide by 10 by 10, and then square root of 2 is given. Let's really calculate the value. So let's do it. So what I want to do is this one. Basis I will call it from some function. This is the easier way. Linear combination of these things. And then, yeah, my design is a little bit messy because I did not design completely modularly, so it is a little bit dependent. And I frankly do not know how to change it, but roughly phi of like 1 over square root of 2, 1 over square root of 2 is given. Then what kind of value can you get? We don't know, right? Once we plug in. But that does not depend on the mesh size. Our basis function kicks in to calculate the value. So the best place that I can change might be around here, linear combination, or so you may consider questions while I'm trying to check possible changes. Basis function may have something. I will completely destroy unnecessary things and then calculate phi value. Phi function requires R, phi R, point vector L. Phi 3 of, for instance, let me check square root of 2 and square root of 2 first. This is about 0.7. Then 1, 2, 3, 4, 5, 1. And then 7, phi 7. Phi 7. And then phi function has point information. So like 1 over square root of 2. And then phi of 1 over square root of 2. And then 0.02. So is this fair enough? We are calculating phi 7 of this point. So we don't have to really create the new mesh to handle this problem. We just call the basis function at this point to find the value of this. So let's do it. So this is the phi val function. So let's change it to phi val. Phi val of like 10 by 10 with 1 and 7. So this is the phi value. So this is, you don't have to really refine your mesh to find this value. Because you have a basis function, no matter what point is given, we can calculate phi something of this thing at any point. But if you don't have basis function, then it's very difficult to determine the value like this. So my question is this: can you determine phi 7 of point like so? This is a question. Can you calculate this thing? Generally it's tough, right? Generally it's tough. But now we don't have to worry about this kind of thing at all. Our design does not really depend on does not depend on the number of steps. Only depends on the subdivision and so on. So assume that you ask to handle and find the value at this point, and you don't have to worry. You can just use the program or basis function to find this. So please browse the design, and of course I'm not saying this is the best design, just one working design. And you may have a better idea to improve these things and then later do it. But roughly I will review one more time. I just determined the boundary, right? X boundary, Y boundary, and the right hand side function, and then boundary function, right? Boundary function, and then the dx side, right? Delta x side, delta y side, right? East direction and south direction. And then I replace these things by interior, a number of interior points, right? Number of interior points instead of just interval number. And then I created small steps in x and y, created this kind of list, and then I used this kind of list to create the vertex position, right? Vertex position is completely created. And then after creating the vertex position, I handle the boundary points. And after handling the boundary positions, I create the link information. After creating the link information, I populate A matrix. After populating A matrix, I do the calculation at the boundary to determine Cij at the boundary, right? Ck at the boundary. Coefficient at the boundary can be easily determined by just boundary conditions. After populating the boundary, I calculated B matrix, right? I calculated B column vector by just adding this Ck times Ak with minus sign, and then I solved it. This is it. After this, now basis function kicks in. Linear combination of the basis function with the Cj will do it. So to do these things, I learned MATLAB a little bit and then spent time, and then it took about 3 hours to do it. But debugging may take more time sometimes, debugging and then checking some malfunctions. So roughly we are done, and next time I will answer questions and then review. So if you have any questions, you bring and then ask me. And I will be here until 20, so you can still ask questions personally.